The following program is a production of the Fairfax Network. In conjunction with the Virginia Satellite Educational Network.
Hi, I'm Bradley Fields. I'm here to help uncover some of the mysteries of mathematics. But since I am a magician, I thought I'd start with the famous mystery of the equals and the unequals rope. It goes something like this. We have a short piece, we have a medium-sized piece, we have a long piece. It's told in an ancient papyrus that just because things look different doesn't mean they really are different. You could have things three different sizes, but on another plane of existence, they're really all the same. Three ropes all the same size. At least that's how they really are, but on this plane of existence, the one we live on every day, or the one we live in every day, things look and seem quite different. A long one, a medium one, and a short one. Well, that's the mystery of the equal and the unequal ropes. Now let's go over to Tim and find out about probability. Tim?
Thanks, Bradley. Yes, we are here today to discuss a very important math concept called probability. I have a few of my students here to join in on the discussion. We're actually going to talk about two types of probability. One is theoretical probability, and the other is experimental probability. Okay? Now, to begin our discussion, I'm going to get our friend Pascal the Bunny to show us the definition of theoretical probability. Pascal? As you can see, the definition of theoretical probability is the probability of an event happening is equal to the number of favorable outcomes over the number of possible outcomes. Now, favorable outcomes simply means the thing that we want to happen, and possible outcomes means all the total things that could happen. So I have some things here I want to work with right now. I have an oversized quarter, Lori. Okay? Take a look at this. What are the possible outcomes that we could have if I were to flip a quarter up in the air and let it land?
Well, there would be two, because it can land on heads or it can land on tails.
That's exactly right. There's only two possibilities unless something funny happened, like it landed on its edge, which we're going to say won't happen. Okay, have you ever played in, say, a soccer game and you went out on the field before the game to flip the coin to find out which team, starts? Okay, what do you like to call?
Heads.
Okay, so let's talk about the theoretical probability of you getting a heads. What would it be?
1 out of 2, because heads, my favorable outcome, it can land on it once out of the possible outcomes, which are 2, heads or tails. So 1 out of 2.
You're exactly right. Okay, now I also have here on the table a spinner, and I'd like to look at that next. All right, Eric, I'm going to go to you. Let's assume that all the numbers that are on the spinner are equally likely to come up if we were to spin the spinner. All right, I'm going to ask you, what is the probability of getting an 8?
1 out of 8, because there's one favorable outcome and there's 8 possible outcomes.
Well, you're exactly right. There's only one 8 on there, isn't there? Mm-hmm. Okay. Brian, let's go to you now. I'm going to ask you a little different question. Brian, what is the probability that you would get a red number?
Well, it would have to be 4 out of 8, because there's 4 favorable outcomes, the red numbers, and 8 possible outcomes, which are the rest of the 8 numbers.
Okay, altogether there's 8 numbers on the spinner. Now, you express that as 4 out of 8, okay? Now, with probability, just like we work with fractions, we can simplify that. Do you know what the simplified fraction for 4/8 is?
It would be 1/2.
Okay, and how did you get 1/2?
Well, you can divide 4 into 4 once and 4 into 8 twice.
Excellent, okay? So we could express this probability as 1 out of 2 for getting a red number, all right? Now, in addition, just like with fractions, we can change them into other forms, all right? Do you know the other forms that we occasionally write for fractions?
Well, there's 2 other forms,
What are
and
they?
one is decimals and the other is percent.
All right, so you said that the probability of getting a red number was 1 out of 2 when we simplified it. And what is the decimal equivalent for 1 out of 2?
0.5.
Excellent, okay. And you also mentioned that we could write that as a percent?
Mm-hmm.
And what percent would that be?
It would be 50%.
Very good. So you should know that when we deal with probability, sometimes we will see it in fraction form, as 1 out of 2, or we might see it in decimal form, and we would say the probability of a red number is 0.5, or we might even see it as a percent, and we could say there's a 50% probability of getting a red number. Very nice. All right, I'm going to go to Brina now. Brina, look at that spinner carefully. Okay? Brina, what is the probability of you getting a 9?
Well, since I don't see a 9, I guess it's 0 out of 8.
That's right. Whenever you have a 0 probability of an event taking place, we call that an impossibility. It can't happen. And we're certainly not going to get a 9 on this spinner, are we? Lori, let me ask you a different question. What is the probability of you spinning a number 1 through 8 inclusively? I mean, what is the probability of you getting 1, 2, 3, 4, 5, 6, 7, or 8?
Well, since there's 8 of our favorable outcome, so it would be 8 out of 8 because out of 8 possible outcomes.
Okay, anywhere you go with the spinner, you're going to get one of the numbers that's a favorable outcome. Now, when that happens, oh, by the way, what is that simplified? What is 8 out of 8 simplified?
That equals 1, which is 100%.
Exactly. So when we have a 100% probability of an event, we say it's a certainty. Okay, I'm going to move my spinner here. Now, with the help of our computer, we have a hat with colored balls. All right, Eric, let's take a look. If I asked you to reach inside that hat and pull out a red ball, okay, what would you say the theoretical probability would be for that event happening?
5 out of 10 because there's 5 red balls out of the 10 balls together in the hat.
That's exactly right. Oh, and remember, we can simplify it, so 5 out of 10 would simplify to?
1/2.
All right, and we could also write it as a decimal, which would be?
0.5.
And do you know the percent as well?
50%.
Excellent. Okay, Brian, we have some other colored balls in there. What is the probability of getting a blue ball, Brian?
Well, since there's 3 blue balls, that would be 3 favorable outcomes over the 10 balls altogether, which is the possible outcomes.
That's right. You have a 3 out of 10 probability of getting a blue ball. Now, is that simplified already?
Yes.
Okay, but we could express it as a decimal, which would be?
0.3.
And as a percent?
30%.
Excellent. All right, we have one more colored ball in there. How about you, Brina? Brina, what is the theoretical probability of reaching in and pulling out a green ball?
Well, since there's 2 green balls and altogether there's 10 balls, I guess it's 2 out of 10.
Excellent. And of course, we can simplify that too.
1/5.
And do you know the decimal equivalent for 1/5?
0.2.
Right on. Excellent. And how about the percent?
20%.
You guys really know your fractions and decimals and percents well. Okay, well, I think you get the idea on theoretical probability. I think it's time that you practice some theoretical probability on your own. You've been working with theoretical probability, but there is another type, experimental probability. Now let's think back to when we did work with theoretical probability. Lori, did I ever let you flip that coin?
No.
No. And when we had the spinner in front of us, did I ever let anybody spin the spinner?
No.
And when we had our hat full of colored balls, did I let anybody reach in and take a colored ball? No. We were exploring theoretical probability, and when you do, you talk about the number of favorable outcomes over the number of possible outcomes in theory. We look at the possibilities and then make our decision. Well, in experimental probability, it's different. We actually perform an experiment. Now, we're going to perform an experiment, but before we do, I'm going to get Pascal to help us out with the definition. Pascal? As you can see, the definition of experimental probability is defined as the probability of an event is equal to the number of times the event happens over the number of times the experiment is done. All right, I think we're ready to begin our experiment. I have here a box of pretend cookies. And inside our box, I have 2 oatmeal cookies, and I have 4 peanut butter cookies, and I have 6 chocolate chip cookies. Okay? Now, we are going to actually perform the experiment 24 times. Okay? And we are going to replace the cookies each time back into the box. Okay, and that's why we're using pretend cookies. All righty, I think we're ready to go. So we're ready to perform our experiment. Lori, you're first. Reach into that box and pull out a cookie.
Chocolate chip.
Peanut butter.
Oatmeal.
Chocolate chip.
Chocolate chip.
Oatmeal.
Chocolate chip.
Peanut butter.
Peanut butter.
Chocolate chip.
Chocolate chip.
Chocolate chip.
Peanut butter.
Peanut butter.
Well, we've completed our experiment, and thanks to Pascal, we have a very nice tally chart to view. I should mention that our experiment was an example of independent probability because we replaced the cookies each time before we drew a second time. Had we not done that, that would have been dependent probability, and that's another topic we don't have time to discuss today, but it is very interesting. All right, let's go to you, Eric. Let's talk about chocolate chip cookies first. What would you say the experimental probability for the chocolate chip cookies was?
Well, we performed the experiment 24 times and got a chocolate chip cookie 11 times. So I think that the probability of pulling a chocolate chip cookie would be 11/24.
That's right. It happened 11 times out of 24. How does that compare to the theoretical probability? How many chocolate chip cookies did we start with?
6.
And how many were there in all?
There were 12.
That's right. So what would you say? Is that pretty close?
Yeah, that's very close because 6/12 can also be represented as 12/24, which is very close to 11/24.
You're right. Very nice. Okay, Brian, how about the peanut butter cookies? What was our experimental probability for peanut butter cookies?
Well, since during the experiment we got 8 peanut butter cookies out of the total 24 times that we did it, it would have to be 8/24.
That's right. And the theoretical probability, how many cookies were in there? Peanut butter cookies?
4.
That's right. Out of?
12.
Okay. And what do both of those simplify to?
1/3, which is exactly the same.
Terrific. Okay, Brina, what about the oatmeal cookies? What was the experimental probability for them?
It was 5/24.
Okay. And our theoretical probability, how many oatmeal cookies were in the box?
2.
And there were a total of how many?
12.
All right. How do those two probabilities compare?
Well, 2/12 is also 4/24, and so they're pretty close.
That's right. 5/24 would be very close to 4/24. So we have shown here that experimental probability usually comes out pretty close to the theoretical probability. We've had a lot of fun today. If you have some coins, a spinner, or even some pretend cookies, you could perform some of these experiments on your own. Well, thanks for watching, and I hope you've learned a lot about probability. Right now, I think it's time for some real cookies. What do you think?
Yeah.
Okay. Now, before we eat these cookies, though, Lori, I got a question for you. What is the probability of me getting a chocolate chip on my very first bite?
That's a stale joke, Mr. Woolsey.
Okay, let's dig in.
Math Magic, an exciting magic show all about math, is available for school assemblies. For information, call Bradley Fields Magic Productions at 1-800-449-MATH.